Hello and welcome to our video on looking at some more in-depth approaches to the subatomic particles. Where we left off was we just introduced where the subatomic particles were developed, how they were experimented on, and how they were discovered. The three subatomic particles that we discussed, the proton, the neutron, and the electron. We have, again, table 1.1 in your textbook that shows the mass in kilograms, which is our SI unit, the actual accepted unit for most scientific works. But again, in chemistry, we don't really use the kilogram that much when we're studying matter at the subatomic level. So we have introduced the atomic mass unit, and that's what we're going to talk about a little bit early on today. We also see the relative charge of the proton, neutron, and electron. There was a calculated charge in coulombs, which is again an SI unit, but again relative for us. Instead of having that 1.6 times 10 to the negative 19 as the charge in coulombs, we'd rather have just a relative charge. So the numbers that we will use most often are the AMU units and the relative charge units. The relative charge is a unitless value, +1 for the proton, -1 for the electron, and 0 for the neutron. Now with our atomic mass unit, or AMU, it's important to be able to say, why do we use it? What's the purpose? And the purpose is, one, to show the actual drastic difference between the proton, neutron, and the electron mass. And it also helps simplify our calculations. Sometimes it's abbreviated AMU or just simply U. What we'll see a lot in chemistry is the idea that we're really, really lazy. Chemists like to abbreviate things as much as possible. And so the atomic mass unit is our first type of way of normalizing a mass to better suit our needs. Specifically our needs of looking at the subatomic realm without going so drastic, 10 to the negative 27 kilograms. There's no way we're going to measure that on a scale. So we'll see, again, as we dive into this video, we'll see how we actually can measure things in the lab, but most often in our theoretical purposes, the mass in AMU will suffice. Okay, some atomic symbol notation. What can we do with that information of the subatomic particles? Well, the proton count itself defines the element. Proton count is the most important factor in defining what atom or element we are working with. And that is what we call the atomic number. We're going to have a couple of definitions here as we get through understanding how we write out elements in our shorthand way. Atomic number, or even abbreviated the Z. It could be referred to as the nuclear charge. We do know that in the nucleus we have protons and neutrons. The mass, protons and neutrons, are contained in a very small, highly packed, dense section of the actual atomic structure. That's what Rutherford's gold experiment determined. And so when we think about that nucleus, it contains protons and neutrons. The protons being the only thing that is charged, so we can call it a nuclear charge. We can write an elemental symbol as X. And from that elemental symbol, we can get a name. We'll talk about those in just a second. If we wanted to write a little bit more expression there, we could put Z in the bottom left-hand corner. That's the atomic number, the number of protons. We can also write at the top left-hand corner A. So another definition we have here is the actual mass number, which is actually defined as the protons plus the neutrons. What is the mass of the atom that we are looking at? Right, so Z is our number of protons, A is our mass number, the protons and the neutrons. The chemical symbol is always linked with our Z, our atomic number. The mass number can change, and we'll be able to discuss how does the mass number change. It won't be because of the protons, it will be because of the neutrons. Another way to write a shorthand atomic symbol notation is by writing the symbol dash the mass. Because the atomic number and the symbol are linked, you don't often have to write Z anywhere. It's optional. You should know based off of the symbol how many protons are in that element, but the mass can change, and that's based off of our neutrons. And so when we're looking at a couple of different ways to write out some informational tidbits on our atomic symbol notation, we could see either one of these. So for instance, we could see chlorine 37 right there. When we think about chlorine, we can look up on a periodic table and see, oh yeah, chlorine right there is atomic number 17. You don't have to write it, because I would know just by looking at that atomic symbol, the proton count is 17. This is a neutral element, so I have to be balanced with my protons and my electrons. And my neutron count, I would simply take the mass minus the number of protons to solve for that. So we can look at that atomic symbol notation that said Cl37 up there and know a lot about the element that we are discussing. Another way to write that would be Cl-37. You will always have a periodic table with you. I do not need you to memorize this beautiful, beautiful thing. We will dive into the periodic table more and its structure and how Dmitry Mendeleev, a Russian scientist, developed the periodic table just over 150 years ago. But at this point, we just want to be able to look at it, to find some important information, see what's on here. So a couple of things that we can look at. I'm just going to bring up hydrogen right over here. What we see in this box up for hydrogen is that it has a little 1 up there. That is the atomic number. Notice how the periodic table is organized by atomic number. If we read how we normally have read, left to right and top to bottom, 1, 2, 3, 4, 5, 6, 7, 8, all the way down to 118, which was one that was newly discovered in the past year. Now, yes, the structure of this periodic table might look a little weird. Why are there some gaps? We will dive into that in just a couple of lectures, and we'll see all of the wonderful things that we can deal with. Notice down here, right there, it says underneath the name hydrogen, it says 1.01. Now that is not the mass number. The periodic table does not contain mass numbers. What it does contain is an average isotopic mass. This mass is in AMUs. We aren't looking at these masses as kilograms. They are in the atomic mass unit itself. But what's important to be able to note is it's not a whole number like our mass numbers. Mass numbers are whole numbers. To a point, what we want to think about is when we are looking at our atomic symbol notation, and the mass number itself is the simplistic value of protons plus neutrons, an average isotopic mass introduces our new discussion of isotopes. Now, isotopes are varying numbers of neutrons. And when different elements have different numbers of neutrons, they could have the same proton count. I'll give you a couple of examples in just a second, but those relative number of neutrons could be different, and it actually changes the mass, it changes the physical properties, it changes everything about the element. We're going to see how to calculate the average atomic mass. It's with using this style calculation. Here is the formula. Atomic mass is equal to sigma, which is the sum of all of the masses times their abundance, their natural abundance. So if you have 2 isotopes in a given element, or 3, you times each mass by its own abundance and then add up each of those. So an example, chlorine 35 has a mass very, very close to 35. We're trying to be as specific as possible with our data. So we'll give you the actual data that we would see from a mass spectrometer. And the abundance, or the isotopic abundance, which is always given in a percentage, 75.77%. Now, chlorine 37 is also an isotope of chlorine. It has a mass of 36.97 AMU and an abundance of 24.23%. When we want to plug these in to the calculation, it is very important to take each step-by-step calculation. We would take the mass of chlorine 35 and multiply it by its abundance. Now, we don't want a percentage at the end of the day. We want our units to be in AMU. So change that percentage to a decimal point. Then we'll do the same for chlorine 37. Now, if you've taken this class before, or you watched the intro video to significant figures, you know that when we have different orders of operations here and different mathematical operations such as multiplication and addition, we need to take one step at a time in order to truly understand what sig figs we have. So I'm going to do the multiplication first, 4 sig figs and 4 sig figs. So my answer here should be 4 sig figs. 26.50 AMU plus, again, 4 sig figs and 4 sig figs, 8.958 AMU. Now, when I'm changing my operation to addition, I need to remember when adding, I don't look at the number of sig figs, I actually look at the number of decimal places. And that's how many I need to report the smallest amount. So I have 2 decimal places adding up with 3 decimal places. So my value should only have 2 decimal places. I'm only as accurate and precise as my data. So there is our calculated atomic mass for chlorine. Not chlorine 35, not chlorine 37, average atomic mass for chlorine element. All right, so that's why it's important to be able to use this value on the periodic table and to be able to calculate it from given data.